Hello, everyone. My name is Rodrigo Castellanos. I am a postdoc at NC State University working with Professor Robert Heath. And today I'll be presenting our work that was accepted into Asilomar, which describes a new process for characterizing arrays in terms of what we're calling the electromagnetic manifold. And the motivation for this work really comes from the observation of the discrepancy between the antenna and electromagnetic theoretic way of characterizing arrays versus the array processing way of characterizing antennas. If we take a look at how antennas are implemented in real devices, right, there's generally a number of different antennas that are present in even a single device, right? Generally, you would have a separate radio available for whatever frequency bands the device is operating at, and each of those arrays for those different bands would have different configurations. They would have different operating frequencies, different gain patterns, potentially different polarizations, right? And so each of those arrays would need to be modeled separately electromagnetically. And in terms of coupling, right, if we look at the interactions between the arrays, there would not only be interaction or coupling between the antennas within each of the arrays, but also among the different arrays with each other, right? And this is because antennas are complicated devices that not only respond to their excitations, but also to the environment around them. And the environment can actually have a significant effect on how the antenna radiates or propagates energy. Right, and let's contrast this with how array processing analyzes antenna arrays, right? Generally, in array processing, we assume that we have point sources or point antennas that are uniformly spaced in some sort of uniform geometry, right? And this leads to mathematically tractable models, right? And the analysis can be quite insightful, right? But it is not as complete as the electromagnetic picture, right? We're missing important components here like the polarization, the gain pattern, and even arbitrary configurations of antennas, right? And so what we're aiming to do here is to combine this array processing perspective, right, where we have a way of characterizing the response of the array mathematically, right, and analytically, with the electromagnetic-based approach, right, where we take into account all of the non-ideal behaviors of antennas. Right? And a few applications where this is relevant are recent and emerging in modern deployments, right? For example, if we look at advanced antenna arrays, right? In the context of wireless, modern antennas can actually be reconfigured to dynamically adapt to the propagation environment. For example, we could have a polarization reconfigurable array, as shown here on the left, where each of the antenna elements could adaptively change its polarization to better combat channel depolarization. Right, on the right here, we're showing a gain pattern reconfigurable antenna that is implemented as a metasurface type leaky wave antenna. Right, so here on this design on the right, we actually have a number of unit cells, all of which are fed by a single excitation, right? But by adapting each of those different slots through an external controller, we can actually adapt how the antenna itself radiates energy. Another application where the antenna effects can be important is typical cellular deployments, right? And this is because array sizes are growing so large that the near field or the boundary between the near field is actually expanding to the typical distances that would be observed in microcells, right? And this is important because when we're looking at far field versus near field, the propagation conditions, right, can look different. The wavefronts will look planar in the far field and they will look spherical in the near field. But there's also issues with polarization in the near field and gain patterns in the near field that need to be accounted for when we are communicating in the near field of an array. Another scenario that might be relevant for characterizing antennas in a more realistic fashion is when looking at exposure considerations. So if we look at devices, particular devices that are operating close to humans, right? All of these devices are exposing users to non-ionizing radiation. And the important issue here is that all devices are subject to regulatory constraints on how much radiation they expose users to, right? And this is because the effect of RF waves impinging on users is thermal heating, and we want to limit the thermal heating for safety reasons. And in this case, it's important to take into account the different effects of the antennas, including the gain pattern and the polarization, because these can have a significant impact in how the users absorb energy, which can lead to drastically different ways of signal processing, right? Is if we're trying to limit the amount of energy that's being absorbed by the users. So here it's important to take into account that not all antennas are equal, so that we can properly measure exposure and properly design the system to be exposure aware. Now, if we're looking at prior work, there have been attempts at characterizing antenna effects in a variety of fashions, right? One is incorporating the effects directly into the channel, right? That would be incorporating the gain into the channel, maybe the polarization by having a dual polarized channel. And these are typically designed for far field applications, right? There's also emerging electromagnetic-based models which aim to characterize the array closer to the source. But the issue with these prior works is that most of them do not simultaneously characterize all of the important effects simultaneously. And what we're calling important effects here include polarization, coupling, gain patterns, near field, so on and so forth, right? All of these effects are important, but most works tackle these effects individually or maybe lump models together to account for all of them simultaneously. Now, what we're proposing to do with our framework here is to characterize all of the salient antenna effects, right, including polarization, coupling, near field, and so on, as close as possible as we can to the array within a generalized framework that can account for different array geometries. And so this is quite a lofty goal here, but the contribution that we're going to show in this work is that we're able to, with a particular model that we're calling the electromagnetic manifold, characterize the radiated electric field of the array in terms of the signal vector, again, accounting for all of these key issues that we've discussed. The way we do that is we look at the electromagnetic characterization of an antenna and try to incorporate this into an array processing framework. So in terms of electromagnetics, the radiation or the description of an antenna is fully characterized by its current distribution. When we excite an antenna, it induces a 3D current distribution along that antenna element. And if we know that current distribution using Maxwell's equations, we can calculate both the radiated magnetic field and the radiated electric field. Now, the issue here is that this current distribution can be difficult to obtain in a continuous form, that is, knowing the current distribution at each point along that antenna. But typically, electromagnetic software will discretize the surface into a mesh and obtain a sample of the currents along that surface here. And we can actually leverage that to form an array processing kind of framework for the antenna itself. So the way we'll characterize the antenna is in terms of this electromagnetic framework where we discretized the current distribution along that antenna. So let's say we take this antenna and we break it up into small pieces such that in each segment we have the following key assumptions satisfied. The first one is that the current is relatively uniform along that segment, right? And the second is that the segment is small enough that it can be treated as a point source. And under these assumptions, the segment becomes equivalent to something known as a Hertzian dipole. And the Hertzian dipole is really the fundamental building block of radiating surfaces in electromagnetics. And when we have this description, we've now turned the antenna, right, which is a contiguous body, radiating body here, into an array of electromagnetic point sources. And from superposition, by taking into account the radiation of each of those segments, we can equivalently characterize the radiation of the antenna. But to characterize an array using the same framework, the process is functionally the same. If we have n antennas in our array, we can discretize each of those antennas separately, right, to obtain arrays of Hertzian dipoles for each of those antennas. And if we can describe the radiated field from each of those Hertzian dipoles, right, in this extended array of Hertzian dipoles, then we would equivalently characterize the radiated field from the array. Now, the two steps needed to measure this radiated field are: one, we need to know the current distribution on the array, and two, we need to convert that current distribution to the electric field. In order to obtain the current distribution on the array, what we do is we would obtain some measurements from electromagnetic simulations and then weight them appropriately by the weight vector. We do this by forming what we're calling here the effective array moment matrix. And this is a matrix which in each of the columns, we're assuming only a single antenna is excited here, right? So for example, in the nth column here, we would excite the nth antenna in the array. And this vector here would include all of the currents in all of these Hertzian dipoles in the entire array. And we do this because from mutual coupling, right, even if we're only exciting the nth antenna element, we'll actually observe currents on all of the antennas themselves, right? And so from electromagnetic simulations, we would assume a unity excitation on the nth antenna, measure the current distribution, and that would be the nth column, right? And so by exciting each of the antennas separately in our array, we would obtain capital N columns here in our effective array moment matrix. And weighing that by our weight vector here, that would effectively give us, from linearity and superposition, what the actual current distribution here is on the array. Once we have that current distribution, the only remaining task is to map that to a radiated field. And the way we do that is from these two matrix transformations here. One which we're calling the current to field transformation that effectively takes the currents that we're observing on those Hertzian dipoles and maps it to an equivalent radiated field that we would observe from that Hertzian dipole. The second component here is the rotational coherence matrix. And this is accounted for because the current to field transformation is assuming local coordinates for each of those Hertzian dipoles. And so we want to make sure that we're adding all of the field components in the same spherical basis, right? And so as long as all of the components are aligned, we can superimpose them together to obtain the radiated field. Now, each of these components here, combining the rotational coherence matrix, the current to field transformation, and the effective array moment matrix, combining those into a single matrix, we obtain something known as the electromagnetic manifold. And this has the same description or interpretation as you'd get in array processing, where we have the steering vector, right? In array processing, the steering vector maps the array excitation to the field observed in a particular point, right? And we're seeing the same thing here. We have an electromagnetic manifold, which maps a particular excitation of the array to the field observed at any point P. Now let's compare this electromagnetic manifold to other notions of the manifold, right? For example, in an isotropic setting for array processing, we could describe each of these antennas in terms of point sources, right? And there, the only thing that we would need to take into account is phase differences and potentially amplitude differences between different elements here. And using this, we could formulate something known as the isotropic manifold using this steering vector shown here. And to obtain the array pattern, we could apply the principle of pattern multiplication as long as each of those antennas have the same pattern here, right? So if we assume that each of these antennas have the same pattern and they don't affect each other, then we could use pattern multiplication to multiply the array factor, right? That's essentially the gain pattern observed from the steering vector and the excitation times the element pattern of a particular element to observe the overall array pattern. Now, the key issue here with the pattern multiplication approach is that generally the steering vector would only apply in the far field, especially if we're not accounting for amplitude differences. And depending on how we're measuring these element patterns, it would not be able to account for near field effects, polarization, and even mutual coupling, right? Because we're treating each of these antennas as having the same pattern and having no effect on each other. So this approach can work if the assumptions hold, but if they don't, then there are non-ideal effects that arise. A more accurate approach here would be something known as the embedded manifold, right? This is an extension of that pattern multiplication approach, where instead of saying that each of the antennas has the same gain pattern, we're now allowing each antenna to have a different gain pattern, right? And this would be true because the presence of other antennas in the array will actually affect the gain pattern of any individual antenna, right? So if we call G of n the embedded pattern of the nth antenna, right, that is when the nth antenna in the array is excited, we could form an embedded steering vector that incorporates those gain patterns, right, and those phase differences. And by combining those appropriately, we could obtain the radiated field at any point in space. The issue with the embedded manifold is that to measure, right, the radiated field, we would actually need the embedded patterns for all of the antennas at all points in space, right? So this would be a large amount of data needed to characterize the array. And in general, the embedded patterns are only obtained in the far field, and they can be difficult to obtain. For example, in a large array setting, the embedded pattern would be difficult to measure even in simulations, just from the sheer amount of elements in the array. So while this is a more accurate approach than the isolated manifold, it's not always tractable, computationally tractable, and it's also not as analytically mathematically tractable as the Now, another approach that we could use to characterize the array is something known as the embedded manifold. And this is a direct extension of the isotropic manifold, where we're now allowing each of the antennas to have different gain patterns. And the reason why this is important is because from mutual coupling, we'll actually observe different gain patterns from each of these antenna elements just from the presence of other elements in the array. So if we call G of n this embedded pattern of the array when only the nth element is excited, we can form an embedded steering vector where we're including those gain patterns into the steering vector along with those phase differences between the different array elements. And using this embedded manifold, we could then characterize the radiated field from the array. The issue here with the embedded manifold approach is that to characterize the field at any point in space, we would need the embedded pattern of each of the antennas at all points, right? And this can be a significantly large amount of data that we would need to just characterize the array. Because of this reason, the embedded manifold is generally too computationally complex in terms of the data that we would need to characterize. And so most studies will either simplify the embedded manifold by ignoring coupling, right, and using isolated patterns and reducing the pattern multiplication, or using only the far field patterns for the embedded pattern here. So this P here would only depend on the direction and not the distance from the array, right? And so while it might be accurate, it's not as mathematically tractable as our proposed approach here. And so we performed some simulations using the MATLAB antenna toolbox to compare the accuracy of our proposed model of this electromagnetic manifold against these two benchmarks, the isolated manifold, which uses pattern multiplication, and the embedded manifold. And here we're showing two proposed approaches known as the near field and the far field electromagnetic manifolds. The only difference here is in how we're treating the radiation from the Hertzian dipoles themselves, right? So in one, we use the near field expression for the Hertzian dipole, and in the other, we use the far field expression for the Hertzian dipole. In both cases, though, we can observe that the proposed approach exceeds both benchmarks in terms of the relative error between the true observed electric field from the MATLAB simulations and the proposed models, right? So the proposed near field manifold always outperforms the isolated manifold and even the embedded manifold. And the proposed far field manifold is actually performing relatively close to the embedded manifold here, right? So our proposed approach is achieving very low errors in estimated the simulated values. And something interesting that we're showing here is that depending on the assumptions of the array, we're actually observing different behaviors for the error, right? At half wavelength spacing, the isolated manifold performs quite poorly because of significant coupling between the antennas here in the array, right? But if we increase the spacing to 5 wavelengths, we're actually seeing an improvement in terms of how the isolated and the embedded manifolds perform. So they achieve lower errors, again, compared to the proposed approach here. Now, one nice thing about our proposed manifold here is that it can account for various types of antennas without needing to necessarily incorporate the gain patterns of those antennas, right? So here we're showing the results for half-wave dipoles, but we can equivalently consider bow tie antennas as well, right? And we can do the same simulations, and using the same framework, we can characterize the radiated field from those triangular antennas. And again, we're observing very low errors from the proposed approach compared to the baselines. One important thing to note here is that the proposed approach is achieving higher errors than the embedded manifold at certain distances. And this is expected because the embedded manifold is actually using true measurements from MATLAB, from the MATLAB estimated values, right? So we would expect that in the far field, the embedded manifold performs the best, and because the error of the estimated values and the true values will converge to 0 here. But regardless, the proposed manifold is achieving very low errors at all distances from the array. And that's also important to note here. Right. One important aspect of the development here is noting cases in which our approach, this electromagnetic approach, can be simplified to that array processing interpretation of the array manifold. Okay, and the way we do this is we start applying those assumptions that are needed for developing the isotropic manifold. The first is the far field approximation for the Hertzian dipoles, right? And here, essentially, what we're noting is that if we have the angular and radial amplitudes for those Hertzian dipoles, as we increase the distance from the array, those amplitudes of the radiated fields converge to certain values. The angular amplitude converges to a value that's only dependent on inversely with R, and there is no radial component to the radiated field as we go to larger distances from the array. So this far field dipole transform can actually be simplified when the point P is far from the array. And this in essence means that the antenna starts to look more like the antenna, which we've discretized to a number of Hertzian dipoles, starts looking more like a single Hertzian dipole in the far field. Okay? And if we further assume that we don't have any coupling between the antenna elements here, we can obtain a simplification that becomes the isotropic manifold with pattern multiplication here. So if we assume no coupling, which means that when we excite a single element, only that single element is excited, and we simplify based on our proposed manifold here, we can actually obtain the same expression that we would obtain from pattern multiplication, where we have our array factor here with the isotropic steering vector and the weight vector, and the pattern, the element pattern here, which is denoted here as E antenna. So the key part here is that the electromagnetic manifold reduces to the isotropic manifold under uncoupled and far field conditions. And this is to be expected as long as we're using the proper assumptions for developing the manifold. But it's important to note the assumptions that are needed for this isotropic manifold. Right. So far, we've only talked about the development of the model and how it can characterize all behaviors of the antenna in a variety of settings, but it's also important to note what applications could benefit from this manifold approach, right? This electromagnetic manifold. And so one application we'll show here is the use of the manifold for beamforming. So let's say we have an antenna array composed of n antennas, and we have our beamforming vector here, W, that is used to excite those antennas in the array. And the key problem here will be to maximize the observed electric field strength at this receiver, which is located at a point P. And so rather than assuming a particular polarization here at the receiver, we're going to assume an ideal receiver that can actually extract all the power from that electric field, at least in this initial setting. When we do this, we can formulate the the beamforming optimization to maximize that received power in terms of maximizing the electric field strength, right? And we can write this problem in terms of the electromagnetic array manifold here, where we're trying to maximize the beamforming vector subject to some transmit power constraint based on that expression we have here. And the solution to this problem is well known and not something that is necessarily complex here, right? We would essentially perform maximal eigenvector beamforming, but instead of beamforming along the isotropic steering vector, as we would do in array processing, we're now beamforming over this electromagnetic array manifold, right? And when we do this, we're extending the notion that all antennas are equivalent to each other, right? And that all antennas can be treated as equally. And we're including the fact that all antennas in the array can have different characteristics depending on their gain patterns, depending on coupling between them, and depending on the distance of the point P from each of those antennas. So this electromagnetic manifold is a better representation of the induced radiated field from that array. So if we compare beamforming gains obtained from our proposed approach here with the electromagnetic manifold compared to the isotropic manifold, which would be beamforming with the traditional array processing manifold, we can actually observe up to 1 dB gain at all distances, just purely from using a more accurate representation of the array here. And something important to note here is that these beamforming gains are observed directly from MATLAB. That is, we used our framework to optimize the beamforming weights, but then we plug these back into MATLAB to make sure that we're observing the proper values for the gains. And we're still observing around 1 dB gain, again, compared to that traditional benchmark of isotropic beamforming. And here we're showing two different angles for beamforming, and we're showing benefits for both of these, right? So while the optimal beamforming problem solution, right, is the same, it's maximal eigenvector is the maximal eigenvector in each of these cases, the use of a different manifold results in a different solution, and we can actually get more gain from the same array just by taking into account its properties. Right. And so in the future, this is a very general framework for characterizing antenna arrays, right, that we can extend to now characterize more realistic settings for MIMO, right? We could apply the electromagnetic manifold to characterize antennas in the transmitter and the receiver, right? To again account for near field effects when those arrays are close to each other or where we have very large arrays, or to account for polarization differences between the transmitter and the receiver, and even mutual coupling between the antennas and the transmitter and receiver, right? So using this electromagnetic manifold, we can extend the notion of array processing to a more realistic setting that includes electromagnetic effects. And so the next challenge that we're aiming for addressing with this framework is incorporating it into a large MIMO system, where we now have the electromagnetic manifold applied at both the transmitter and the receiver in order to optimize the MIMO system with this new framework. And so in our future work, we're aiming to develop new channel models and algorithms that exploit this manifold structure, and then seeing what insights we can gain from this very general framework. The journal version of our work can be found in arXiv under the name Electromagnetic-based Manifold Characterization for Antenna Arrays. And again, this presentation was based on our paper in Asilomar 2023.